Okay, everybody, it's 1 o'clock. I want to cover this document, which is called inverse trig integrals. I already sent that on Leia. So it's posted on Leia. You can open it if you like. It's about the antiderivative of 1 over root 1 minus x squared and 1 over 1 plus x squared. So you should remember from Cal 1 that the derivative of arc sine x, which can also be denoted by sine inverse of x. So in that case, the derivative is 1 over root 1 minus x squared. So automatically, the antiderivative of 1 over root 1 minus x squared dx is going to be arc sine of x plus c. And we also had this last semester, the derivative of arc tangent of x, which can also be denoted by tangent inverse of x. The derivative would be 1 over 1 plus x squared. Then, automatically, the antiderivative of 1 over 1 plus x squared dx is going to be arc tangent of x plus c. So we know that the domain of arc sine of x is any number between -1 and 1. You cannot plug in any number greater than 1 or less than -1 into arc sine. But the domain of arc tangent would be any number, any real number. Okay, so any questions so far? Okay, let's look at some examples. So we have 3 over 5 plus 5x squared dx. If I factor out a 5 from the denominator, I get x squared plus 1 at the bottom. So the 3 over 5 is a constant. I am dealing with this, 1 over x squared plus 1. And I have the formula over here. The antiderivative of that is arctangent. So the answer is going to be 3 over 5 arctangent of x plus c. Is that clear?
Yes.
Example 2. We have antiderivative of -2 over root 16 minus 16 x squared dx. Okay, so I can see that if I factor out a 16 here, I'm going to get 1 minus x squared. I also remember that root AB is root A times root B. So that means I can write this as integral of -2 over root 16 times root 1 minus x squared dx. But this is just a 4, right? So this becomes -2 over 4, integral of 1 over root 1 minus x squared dx. And this part here is arc sine. So the answer is -1 over 2 arc sine of x plus c. Example 3. You're good with number 2, no problem. Okay, so here we have integral of 1 over root 1 minus 7x squared dx. So if it were just x squared rather than 7x squared, if it were just x squared, then I knew it's going to be arc sine. But now I have 7x squared. What should I do? Here I need a substitution. I'm going to take u squared to be 7x squared. That is, u itself is going to be root 7x. Make sense? I want this to be replaced with u squared, because if I have a situation like this, if I have 1 over root 1 minus u squared du, then I know this is arc sine of u plus c. I know this, so I want this here to be replaced with u squared. So I take u squared to be 7x squared, then automatically u would be the square root of this, which is root 7x. And then from this I can conclude that du is root 7 dx, because root 7 is a constant. Now I have the roots, I have the dx, I always have that, but I am missing the root x, but that's no big deal. I can always multiply by root 7 on top and divide by root 7 at the bottom. And look what happens then. I get 1 over root 7 integral of everything here, the root 7 times dx. That's going to be du. And at the bottom, I have what I needed. I have root 1 minus u squared. So this is going to be 1 over root 7 arc sine of u plus c. Last step, I need to replace the u with whatever u is in terms of x. So we get this. Is that clear? Do you want me to re-explain this, or we're good? Okay. Example 4. We have integral of negative 2 over 25x squared plus 1 dx. This reminds me of arctangent. Only if this was u squared, I could do this. 1 over u squared plus 1 du is arctan of u plus c. So that 25x squared, it's supposed to be u squared. That means the u is 5x. So du is 5 dx. I just need a 5 that I'm missing here. So multiply by a 5, divide by a 5. So this becomes negative 2 over 5 integral of this part is now du. At the bottom, I have what I needed. So it's going to be negative 2 over 5 arctangent of u plus c, but u is 5x. So that's the answer. Is that clear? Any questions? I just want to do one more example with arctan. This one is going to be a parametric one. I'm just using parameters like x is, if you have, what happens if you have x squared plus a squared at the bottom? What do you do with that? So imagine you have something like this. You have dx, at the bottom you have x squared plus 4. how do you solve this? Yes. Generally, if you have dx, at the bottom you have x squared plus a squared. So if a is 2, for example, you get x squared plus 4. If a is 3, you get x squared plus 9 at the bottom. If a is root 5, you're going to get x squared plus 5 at the bottom. Yeah, so this type of integral, how do you solve it? So what you need here is to factor out a squared from the bottom. So you get dx. At the bottom, if you factor out a squared, you get x squared over a squared plus 1. So that's the first step. Now, since a is a constant, I can write this as 1 over a squared integral of x over a squared plus 1 dx on top. At this point, it would help if I do a substitution. I take this to be u, because what I need is u squared plus 1. So I take that to be u, and then du is going to be 1 over a dx. So now I can write this as 1 over a integral of 1 over a dx. At the bottom, I have x over a to the power of 2 plus 1. So it's as if I have 1 over a squared, which is 1 over a times 1 over a. I needed that 1 over a for du, so I moved it here. Is that clear what I'm doing? Now this becomes 1 over a integral of du over u squared plus 1. So it's going to be 1 over a tangent, arctangent of u plus c, which is going to be 1 over a arctangent of u is x over a plus c. So now if you have something like this, integral of dx over, let's say, x squared plus 4, then you can use this like a formula. It's going to be, a would be 2 in this case, because 2 to the power of 2 is 4. Maybe 1 over 2 arctangent of x over 2 plus c. Any questions?